We've studied the mathematics of linear functions, which correspond geometrically to studying lines. But our world is not made up of only things that are straight lines. So how do we get to studying things that curve? Our first foray into curves that are not lines will be the graphs of quadratic functions. A quadratic function is a function f, which takes a real number x as an input and outputs some number that involves x squared. So, for example, if f of x equals 2x squared plus 1, then f is a quadratic. Or if f of x equals x squared plus x minus 3, then f is also a quadratic function. The general form for a quadratic function would be f of x equals a times x squared plus b times x plus c, where a, b, and c are some real numbers. Just like for linear functions, it's often useful to look at the graph of a quadratic function. Looking at the simplest quadratic function, f of x equals x squared, and plotting points x comma x squared, we can see that the graph will have this curved shape, which we call a parabola. We'll see later that any quadratic function will have a graph that looks roughly like this, but possibly shifted or flipped or squashed or stretched. But before we can get to studying that, let's identify some important terminology about the parabola. On the parabola are some important points. One point is the vertex of the parabola. This is either the maximum or minimum point on the parabola, depending on if it opens upwards or downwards. We can also identify the places where the parabola crosses the x-axis, if it does cross the x-axis. These are called the x-intercepts, and they are the values of x where the y-coordinate is 0. So they're the values of x where the equation ax squared plus bx plus c equals 0 is true. Likewise, we can talk about the y-intercept of the parabola, which is the value of y when x is equal to 0. So that's the point 0, comma f of 0. In order to understand quadratic functions, we will need to explore more in depth how to find these points, using techniques like factoring or completing the square. In doing so, we will expand our toolkit of algebraic manipulations that we can do to the expression ax squared plus bx plus c, and this will help us eventually study much more complicated curves.